Welcome to this video on Year 2 Pure Chapter 10 Prep Practice on numerical methods. So question 1, we're asked to use the change of sign method to show that this quartic polynomial has a root between x equals 1 and x equals 2. In other words, that this quartic is equal to 0 somewhere between x's 1 and 2. So what we do is we check the value of this quartic at x equals 1 by substituting at x equals 1 into the quartic, and we obtain minus 2. We substitute the value x equals 2 and obtain the value of 6. And then we must make the statement that because of the change of sign and because the function is continuous, the root must lie between 1 and 2. A quartic is always continuous, but all we need is for it to be continuous between these two values. And of course, it must be because it's continuous everywhere. And because there's a change of sign, that means that our function is negative for one of these values, positive for the other one. And because it's continuous, somewhere between the two, it must be equal to 0, which of course gives us our root in that interval. Question 2 is similar in that it asks us to look at a question where we want to use the change of sign method to show that there's a root for f of x equals sin of x minus 1 of x in radians. And it asks us to show it is the root of 1.1 to 1 decimal place. So how do we do that? I'll just move that. We do that by, again, using the change of sign method. And so we substitute two values into this function. One is the lowest value that gets rounded to 1.1, which is 1.05. And then the boundary of the highest values that get rounded to 1.1 is 1.15. Notice 1.15 is actually rounded to 2, but it's the boundary of values which get rounded to 1.1. So something like 1.1499 would still be rounded to 1.1. And the boundary of such values, the highest boundary of such values is 1.15. And that's what we must use. So feeding in 1.05 and 1.15. Oh, I think I've put them in the wrong way around. So that should be 1.05 here. So feeding in 1.05, we get this value here, which is negative. Feeding in 1.15, just change that here, we get this positive value here. And then by the change of sign method, because it's negative at one value and positive at the other value, and importantly, because the function is continuous in this interval, then a root must lie between these two values, between 1.05 and 1.15. In other words, the root must be 1.1 to 1 decimal place. Now notice this function isn't continuous everywhere. It's not continuous at x is 0, but we only need it to be continuous between these two values to be able to use the change of sign method. So you must quote that using the change of sign method, and you must say that the function is continuous, or in this case, the function is continuous in this particular interval. Question 3, we're asked for a function, this quadratic here. We want to show that when it's equal to 0, that we can rearrange this function from being x squared minus 4x minus 2 equals 0 to being x equals the square root of 4x plus 2. Now, this is a common question when we're asked to use the x equals g of x method, because not all possible rearrangements will give us an iterative formula that works. And so in an exam, you usually will be asked to show that a particular rearrangement can be performed, and then to use that rearrangement to use the iteration formula x equals g of x. So in this case, because we have a square root here, it's pretty clear that we're making this x squared the subject. So if we start with x squared minus 4x minus 2 equals 0, make x squared the subject, and then square root, we can see that it's possible to rearrange this equation, f of x equals 0, to this equation, where we have x equals some formula, which in this case is square root of 4x plus 2. In part B, we could use this iterative formula, starting at a value to then progressively get better and better values if it converges. So starting at x is 0, x0 is 5. We want to find x1, x2, x3, x4. So what we do is put 5 into this g of x formula. So we're going to get the square root of 4 times 5 plus 2, which gives us 4.69. And then we substitute that value into this formula again. So we get 4 times 4.69 plus 2. And that gives us 4.556, and so on until the fourth value is 4.471. And then we're asked to explain whether this iterative method is converging. The other alternative would be diverging, and whether, if it's converging, whether it's via staircase or cobweb diagram. We can see that it's probably converging because the gap between the values is decreasing. And so for the x equals g of x method, that's a strong indicator that it's going to be converging. And then can you see that the values are all decreasing? So it means we have a staircase diagram or method that's being used. If it were alternating between being higher and lower, then that would be a cobweb diagram. Question 4 asks us to use the Newton-Raphson formula, which is always the next approximation is the previous approximation minus function evaluated at xn minus the derivative of the function evaluated at xn. And so if we want to get the Newton-Raphson formula for this f of x, sin of x minus 1 over x equals 0, we need to differentiate it, which gives us cos of x plus 1 over x squared, and therefore the iterative formula for the Newton-Raphson for this particular equation is going to be xn minus the function at xn minus the derivative function at xn. And so if we want to use it to approximate a root near 1.1, then we use the iterative formula by substituting x1 to be 1.1, and then x0 to be 1.1, and then the next approximation will be the previous approximation, which was actually 1.1 here, 1.1, and we want to subtract the function evaluated at 1.1 minus the function derivative function evaluated at 1.1 to give us the next approximation. And then we use that approximation, substitute it in again to get x2. So we have x2 minus f of x2 over f dash of x2, and so on, giving us progressive approximations, which, if it converges, should converge to the root that we want. Calculate and explain whether the estimate x3 gives us a root of this function equal to 0 that is accurate to 3 decimal places or not. So in this case, we want to check this root here and want to see if this root to 1.114 decimal places is in fact the root that we want. So how do we do that? We use the change of sign method, and we look at values which round up to 1.114 and round down to 1.114, and taking the boundary of those values, the lower boundary is going to be 1.1135, the upper boundary is going to be 1.1145, and then if we evaluate the function at each of these, one of them is negative, the other one's positive, and so by the change of sign method, and also claiming that the function is continuous between these two endpoints, that means that the root must lie between them, and therefore the root must be equal to 1.114 to 3 decimal places. Okay, I hope that was useful.